Okay, in this activity, we are going to take a look at hypothesis testing when we are comparing two variances or two standard deviations. This type of testing is going to require of yet another new table, another new distribution. This is called the F distribution. I want to square away our notation here. As to remember that standard deviation squared is variances. And so our larger variance in our formula is going to be identified as variance 1. The smaller one would be variance 2. N1 would be the sample size of the larger variance, and each of these are going to be associated with a population that we're trying to learn about, a population variance that we're trying to learn about. Now we've done something similar where we were comparing two population proportions back when we were dealing with, I believe when we first started into hypothesis testing. We ended up having to deal with pooled proportions. We had to look at the complement. It was a very involved formula. Then when we started looking at two means, comparing two means, we first had to decide, were they independent or dependent? Did we have matched pairs and so forth? And that got a little bit complicated there. You're going to be happy that this is much easier. Our F test is just a simple ratio looking at the two, at the ratio of the two standard deviations, and the larger of the two, variances. The larger variance is going to be in the numerator, the smaller one is in the denominator, and that's it. You're just setting up that ratio and carrying out that division. So we're going to be looking at that and comparing that to a critical value. So in comparison to the other scenarios where we had two sample proportions or two sample means, two variances, two standard deviations are much easier to deal with. One thing, you're looking at this variant or this F distribution, it looks a lot like the chi distribution in that it is not symmetrical. The values of the F distribution are non-negative, or always positive. The exact shape of this is going to be dependent upon the sample sizes of the two different samples that we are comparing. But definitely it's going to be right skewed. One thing I want you to think about is if the two variances are very, very different from each other. In other words, if the larger one is much larger than the smaller one, say we might have a case where the larger variance is 5 point something or other and the smaller one is 1.5 something or other. That larger one is much larger, and the numerator will go into the denominator many times, and so our F statistic in that case is going to be much greater than 1. Whereas if they're very, very similar to each other, let's say it was 3.2 over 3.1, that's not a lot of difference there in the two variances, and so that F statistic will be very close to 1. So we're going to be looking at that, comparing how close it is to 1 in comparison to a critical value. So I'm kind of moving down here. The F distribution table, we use F distribution tables to find the critical values. Now the thing is these tables are long. We have a different table for each alpha. We have one for 0.5%, 1%, 2.5%, 5%, and 10% alpha in each table. Each of these tables are like 2 pages long. In fact, I'm kind of disappointed. Your textbook, the digital textbook, only includes the tables for the 2.5% alpha and the 5% alpha. So I'm not going to ask you to use the tables and learn how to find the critical value using those tables. I will demonstrate that in class so you can see how that works. But for the most part, I will be giving you the critical value that you're going to be comparing to. So you're thinking at this point, why would we even care about standard deviation, comparing standard deviations or variances of two different populations? Let's say that you were in charge of ordering materials for your construction company, and you are getting, a material, plywood, that doesn't seem to be consistent between your two or three different manufacturers. You might do a sample with each of the two distributors that you are comparing and trying to see what is the standard deviation, or how consistent, what is the range of consistency here. And you might set up an F distribution and compare that. But you know that the two variances aren't going to be exactly the same. There's going to be some variance there, or some differences in the variances. But what would be considered normal? And so that critical value is going to help you to decide what's in the normal range and what isn't, which is something we've been dealing with all along. One thing I want to point out is when you are performing a hypothesis test regarding two variances or two standard deviations, there's some strict requirements that seem kind of obvious, the first two anyway. The two populations are independent. Back to my manufacturers, what one manufacturer does not impact the other. That makes them each independent. Obviously, simple random sample, but each of these two populations must be normally distributed. So when you're looking at the different samples from the two different distributors here, I'd want to make sure that I had two normal distributions. If I had one that was really, really skewed, I can't really get a good, reliable variance or standard deviation off a skewed distribution. So these two populations must be normally distributed, and I know that you're going to be asked about that in your My Math lab, so that's key there. Okay, so how do you actually work with the F statistic? Oops, I don't want to go that far high. Okay, again, remember you're looking at the ratio of two variances, and the larger variance is in the numerator, the smaller variance is in the denominator. You're going to need to find the, actually I will find the critical value and give it to you. In this case, this example, I had a right tail test, 10% alpha, degree of freedom for the numerator. In other words, the sample size for the larger variance obviously was 6, and so the degree of freedom for that would have been 5. The degree of freedom for the smaller variance had obviously a sample size of 29. The degree of freedom was 28. So you can see, you will see when I demonstrate in class that finding the critical value is very dependent upon sample size and therefore degrees of freedom. But in this case, our critical value came out to be 2.06. And you don't have to understand that right now other than just know that I will always give you the critical value. The variance for the population of the numerator was 8.82. In other words, the larger variance was 8.82. The smaller variance was 4.82. So when I set up that ratio, the larger over the smaller, I come up with an F test statistic of 1.83, which is not as large as our critical value. When I draw the distribution, and you guys are getting good at doing that, I can see that the 1.83 falls in the normal range. It's not in my rejection zone. This outcome would be considered normal. Whatever kind of a test we were doing, we would fail to reject the null hypothesis because this is not in the rejection zone. The F stat, our F statistic, is closer to 1 than the critical value. And that goes back to that ratio of the larger over the smaller. This is closer to 1 than the critical value. Okay, in another scenario, let's say we had a critical value using a F distribution for a two-tailed test given 5% alpha. My critical value came out to be 3.84. I'm going to give you a standard deviation for each of two populations. Now keep in mind, I'm giving you the standard deviations. The larger one is 3.5, the smaller one is 1.4. When I set up this ratio, I have to stop myself and remember I have standard deviations, and the F statistic is all about looking at the ratio of the variances. So I will have to square each of these standard deviations to get their variances before I divide. You must square first and then divide. In this case, I come up with an F statistic of 6.25, which is much greater than 3.84. When I draw my picture here, I can see that my test statistic falls in the rejection zone. This outcome is statistically significant. Whatever kind of a test I was doing, I would reject the null hypothesis because this F stat is far greater than 1 compared to the critical value.